So now we've talked about using this in the T-cache and using it with fastspin. We're not going to talk about how the FD poison technique works on modern versions of libc. In particular, we're going to talk about pointer mangling. Don't mind the brief part there. That was from some other time I taught this. So obviously the singly linked list has a fairly obvious issue. When I said I can't believe they didn't have a check on this, I was fairly surprised. If you can corrupt a single value in a linked list, then you've totally messed up. So some folks decided to try to change this and added security protections in place that we call pointer mangling. So the idea behind pointer mangling is, what if we change the FD pointer prior to writing it? The hacker will not know how it was changed, and it prevents it from being trivially changed by the attacker as a result. So you could do some sort of encryption, obfuscation, something like that. So what they ended up deciding on was something fairly lightweight, where you can mangle/encrypt the pointer with some sort of secret piece of knowledge. And they decided that instead of having some randomness and having to deal with that, they actually use ASLR. The idea behind this is ASLR already is randomized, and we know this information, and so we can use the properties of ASLR in order to cause havoc on pointers. And this is really useful because if this pointer here, for instance, we go from chunk 1 to chunk 2, is now effectively encrypted, we can't just trivially modify it. Because if we try to modify it and have it go to a fake chunk, when it tries to unencrypt or unmangle the pointer, it's going to be completely invalid, and that causes all sorts of havoc. So how does this mangling actually work? There are two things that really matter here. There is the storage location, aka the place where the pointer is being stored at. So in our previous examples, this would be something like chunk 1. And then there's the pointer itself. So this would be chunk 1's pointer to chunk 2. The way this works is it logically shifts 12 by 12 bits the storage location, and then XORs it by the pointer P. And here's a better diagram explaining. L, or the storage location, is where we're actually storing the pointer at. So this is where the FD pointer is actually located at. And this is going to be randomized by ASLR, of course. And then we shift the actual pointer to chunk 2 by 12. The reason that we do this is because the first 12 bits are going to be constant because of ASLR. Because of just how ASLR works, they wanted to be able to do like bit masking checks on pointers, and so the first 12 bits are actually unaffected by ASLR anyway. And this chunk 2 is the pointer to write. So again, chunk 1 is going to store the pointer to chunk 2. We're going to XOR this together after we shift the address of chunk 1. Don't need that. Cool, so practically, let's go through the numbers. What does this actually look like? Here, we have the pointer to mangle, chunk 2, and then the storage location of chunk. So first, we're going to shift the storage location by 12, which gives us 987,654. Notice that this just kills the first 12 bits in effect. So now, this is how this looks like, and we just XOR everything together. So 987 is, of course, fine. It's just going to go to itself because XOR 0 with anything is going to be anything. And then we're going to XOR the 654 with the 987, and then the 320 with the 654. The demangling is the exact opposite. Nice thing about XOR is that it goes in both directions as long as you use the same values. So we're going to shift the storage location, and then we're going to XOR it by the same values, except we're going to take the mangled value and XOR that by the storage location. And now we get back the same pointer we originally started with, which is awesome. The other protection that this added in these changes is chunk alignment. People were afraid that if people could just brute force this and go into an advantageous spot, kind of have a polyglot type of payload, and it would be totally fine. So the solution to this was to have chunk alignment. By forcing chunks that are being removed to be 0 on 64-bit or 0 or 8 on 32-bit, it makes this pray and spray technique much more difficult, and it makes relative offset tricks on the pointer also not work as well. So this chunk alignment was a very good feature that they included too. And this is just a visual explaining the chunk alignment. So I'm sure you're sweating profusely after seeing this, but there are ways to defeat pointer mangling. It's not the end of the world. So first, relative overwrites with some brute forcing and lux on alignment do work. It doesn't completely solve the problem. Second, if you get a heap leak, this does work. In a lot of situations, you probably needed a heap leak anyway. It does add some complexity that you actually need to know the address of the pointer that you're dealing with. So if you're on a service that's been up for a while, you might need to crash the service, have it restart, and then use it so you can have a deterministic flow. But there's actually ways to decode the mangled pointer. The most obvious one is when it's null. The end of your linked list is just going to be null, and so if you can leak the FD pointer of an arbitrary chunk, then you're totally fine, which is pretty nice. But if you have a mangled pointer, then there are some situations where if it's not null, you can also decode. So if you remember from before, the 987 is in here twice. That's kind of weird. So if I can see this 987 right here, then that means that the next one also may be 987. Because again, these are all just the same bits. So because the top 12 bits are not mangled, if there's not an entire, or if the addresses that we're dealing with are similar enough, then you can actually use this to just decode the whole thing. And you can just do this whole process in reverse, like we did before. Again, there are limitations, though. So what you do is you would take the 987 and the FD3, and you know that the 654 was the one that was going to be on the set 3 right here. So now that you know what that was, you can use that 654 again, and you can do this iteratively until you've decoded the entire pointer. Like I said, with null, it's pretty nice. You just get the whole leak for free because XOR anything with anything is just going to be 0. So that makes this technique like fairly trivial to do as well. Yeah. So I have a tool that I wrote that's on my GitHub that you can use that does this pointer mangling and demangling stuff for you. It's really not that hard though. When I heard of this protection coming out, I was more curious with how it worked. Cool. So that's pointer mangling in a nutshell. We're going to go back to the algorithm, I suppose. We're going to shift the storage location of the pointer by 12, and then we're going to XOR the actual FD pointer by that. And because of some weird properties of ASLR, this causes problems where we could potentially leak stuff. So although we need a heap leak now and have a good idea of relatively where we're at in the heap, it's still doable, and it still works pretty well. So thanks for listening to the pointer mangling talk. Good luck on the next ones.